Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. From today onwards we are going to discuss analysis of flows that are no more isentropic. Okay. And before we go into it, we neglected a whole bunch of terms when we derived the basic equations of flow, mass, momentum, energy conservation equations. So, we will go revisit them and then include those terms and see how the equation looks like and what that is telling us. Okay, that is where we are going to start today. Of course, there is not much change in mass equation. Mass conservation equation, we derived this form. This still remains the same, except for I will write it in one more form. Where this can be clubbed together as total derivative. This is of course fluid mechanics, I will just avoid going into details of this total derivative so much. This is called the total derivative, we will be using it in derivation because it makes our life simpler and writing terms will decrease in number. So, can be written in this form also, and if we say the flow is incompressible, I am going to say density does not change at all, and so this term goes to 0, and that is how we got to incompressible flow, divergence is 0 kind of term. But of course, we are not in incompressible world, we are very much in compressible world. So, this need not be 0. Next is momentum conservation, where we got an expression. This is all I am referring to, like say the 5th lecture or 6th lecture, somewhere at the beginning, where we derived all the equations of motion. I will put this arrow for vector u everywhere. Okay. I have written these extra terms now, which we said were 0 in the previous time when we derived. I have just added these two terms. Basically, this is telling you the total momentum conservation, and the very first time when we derived it, we had this term as dou by dou t of rho u inside the derivative, and I have used this expression inside that to simplify it to this form. I will not go into details of it, it is fluid mechanics, when you go derive the equation for the first time it will come out to be that, and so we will keep only this form. Okay. Now, previously when we were deriving, we said that we do not have any body forces, we set this equal to 0, and then we said that we do not have any viscosity. So, every term in the shear force will have a mu inside it, which is said to be 0, so this term was 0, so we neglected this. Now, we do not want to neglect it, we will just keep it as is. So, basically this becomes our momentum equation. Next is energy. I will write what we had before, and then from there we will add two more terms similar to this. I have written this form here. The left hand side is exactly same as what we derived at the beginning, okay. And we had this term already. We did not have FB and tau terms before. We said that it was 0 and we never wrote an expression for these. We just removed it at the beginning itself in the contribution stage itself, okay. And later we said there is no heat transfer and we neglected this also. That is how we came to this particular form of the equation, okay. One more thing I need to tell you is this FB is body force per unit mass. It is roughly an acceleration term. FB is body force per unit mass, but everything else is per unit volume basis. So I am multiplying by density to get to per unit volume basis. That is how we got to this form. Now I want to rearrange this energy equation so that we can get more information out of this. What is it telling is not very clear if I write it like this. Okay, this is perfectly correct, but it does not give me full information. We will try and rearrange the terms here. I will just take the left hand side of the equation. I will expand it where I will say H is E plus P by rho. I will write it like that. I will see what I am getting. I will do one more thing. I will use differentiation by parts so that I will cut down one step in here. So I am taking rho as one quantity and this bracket as another quantity. I am taking derivative by parts from here. This is coming from the first term alone plus the next term. Again we have to do similar thing. I am going to group this rho u as together and the bracket is another term we will keep. Okay. If I keep the rho u term together, I am going to have ideally I should have del dot of h plus u square by 2, which I want to write. I will write this right here, E plus P by rho. I will put h as E plus P by rho. I will take this E and this u plus u square by 2 together and write it here. We will remember that there is one P by rho term which is left out inside this whole equation. This is one term plus the other term where derivative is on this rho u. Del dot of rho u. Now we will remember that there is a term del dot of rho u times P by rho which is left, which I will write separately, plus del dot of we will just keep it like this. I know I can cancel the density, we will do that later. Now I will look at this expression. I want to simplify it a little bit. I will keep the terms with E plus u square by 2 as a common factor together. If I look at that, that will be this term and this term. If I look at that term, I take this common factor out, what is remaining is dou rho by dou t plus del dot of rho u. That happens to be equal to 0 from mass equation. Okay. So I will just remove that two terms from there. So my left hand side is only these three terms. Okay. So I will continue from there. Oh, by the way, that is the same exercise we did for getting the momentum equation from the previously derived form to present form. Now I will rewrite this again. I want to get to a point where I will go to H naught, the stagnation enthalpy. So I will rearrange this now. Now that it is in a better form, I will rearrange this such that it will be H instead of E in both the places, so that I can write this whole thing as total derivative. Okay. So I will directly write it as H plus U square by 2. We will figure out what is missing after this. Now we will put all the missing terms. I added a p by rho here, so that will come as the next term sitting there, minus rho into dou by dou t of p by rho. I will put a plus inside here, plus u dot del of p by rho plus the final term there, del dot. Since I do not have space, I will cancel the density and write it there. Okay. I have these terms here. Now I can club these two terms together and write it as rho into total derivative of H naught. Okay, these two terms come together to form this one term, minus the remaining terms. We will expand this such that I will have just dou by dou p by dou t and dou rho by dou t. So if I do that, it will be density into 1 by rho dou p by dou t minus 1 by rho square, oh p is also there, dou rho by dou t. These are the terms that come from differentiating this p by rho, that is these first two terms, plus I will keep this term as is, u dot del of p by rho as is. Okay. Now I will expand this term. Actually I like the form, this particular form. I will expand this form here next. I will close this and I will open that one next, where I want to split this term again, rho u together and p by rho together, so that will come and cancel this particular term. That is what I am looking for finally. Okay. So now I will write it as rho u dotted with del of p by rho, that is one term, plus p by rho outside the derivative times del dot of rho u. This is the other form. This is actually coming from this term, but I am using the previous form, which is nicer to expand, and it comes to this particular case. Now I look at this term, this and this, they will get cancelled. Why? This is having a minus sign here. This minus sign, minus rho u dot del of p by rho. This is plus rho u dot del of p by rho. They get cancelled. Okay. Now I look at the remaining terms. If I look at the remaining terms, I will write it one more step. Rho d by dt of H naught minus dou p by dou t, and then this minus and this minus will become plus, and density one of them will get cancelled, plus p by rho dou rho by dou t, that is the only thing, plus p by rho del dot of rho u. This is my left hand side. Now again I am seeing that this plus this together is 0. Why? Again continuity equation. Okay. Continuity equation says this plus this is equal to 0. So p by rho multiplied by 0, these two terms will go away now. So I finally have left hand side to be just these two terms. Now I will bring all the other terms and write it together. My full energy equation will now be rho d H naught by dt now I want to write it with this on the other side, so I will put it as rho dh naught by dt, I have taken the dou p by dou t to the other side, and I have the remaining terms. I will write it as plus rho fb vector dotted with u plus del dot of tau tensor dotted with u vector. There is one more term minus del dot of q. Okay. I finally have this particular form. We won't do any more changes to this. This gives you some more physical feeling. Okay. All this time we said total enthalpy is the net energy content of the fluid. This includes kinetic energy as well as internal energy, thermal energy including the pressure energy. It is having all forms of energy, thermal energy, pressure energy and kinetic energy. Complete set is inside this. So, this is the net content of energy in that particular fluid element. Now, we want to see the change in that particular quantity. If I look at it, it may change, the simplest term is this one, it may change because of, if I call it del dot q is the divergence of heat, this is a heat conduction, heat flux q is basically talking about divergence of heat away from this point. So, if there is divergence of heat away from this point, that is going to have energy loss, so it is negative. Okay. Or you can think about it as minus of divergence is the convergence of heat, opposite of divergence, right, it is converging of heat into that point, that is increasing energy, whichever way you think about it. Okay. That is one term. The next term is here, shear stress tensor doing work with that particular fluid is going to finally generate some amount of energy, because it is increasing the energy of the system by adding work to that particular fluid, that is going to increase energy, and that is this. This is the same kind of work, but done by the body force, the bulk on the bulk fluid itself, and that is given by this term, work done per unit time, that is coming out to be this. Okay. Everything is in terms of per unit volume basis. And finally, there is one more term here which is talking about if I suddenly have unsteady pressure rise, that can also add energy to my fluid. Where have we seen this? We have seen one example where we said there is no heat transfer, there is no body force, there is no shear, but we have a moving shock. If we had a moving shock, then when the shock crosses my current point of interest, then when the shock crosses, I am going to have pressure rising. When the pressure rises, I am going to have T naught increasing, that is how it saw, right. We found that when a moving shock crosses my point, T naught increases, that is directly coming from here. These are the various mechanisms by which we may change energy of the fluid. Okay. Till now we have thought about only simple things, now we will go and look at a little more details of what all other things can change the net energy. Of course, in particular we are going to think about, we will still neglect this body force term, of course you can add it, it is simple enough term. We are going to think about heat transfer and viscous forces. Okay. We will not deal with this complicated viscous force term, I did not explain what this tau tensor is really. I am just going around it, it is not really important for this course, we will just go around it because we are going to work in typically one dimensions, it will come out to be much simpler than this. Okay. If I send an expansion wave, what happens? This will automatically become negative, pressure is going to drop, that will automatically pull out energy from the system. Okay. That can also happen. I may have, if there is a moving expansion, it is going to cool down the gas, it is going to pull out net energy from the gas also, that can also happen. Okay. Any of these can be happening in there. Okay. Next thing we want to do is entropy. So, I will start from the standard thermodynamics form of entropy. When I write this small s, I am going to say it is per mass basis. Okay. We will just work with that form. We had the same convention from the beginning, we will maintain that. dE, which is the internal energy, plus P dV, where dV I will write it as d of 1 by rho, because that is per mass basis volume, so it is 1 by rho. We will rewrite this. Now, this can be rewritten from calculus as minus p by rho square d rho. It can be rewritten like this. Now, we will use this particular definition and we want to write ds by dt, total derivative of entropy, net entropy change in my fluid element. If I write that using this particular derivative notation, I can immediately jump to this particular derivative and I am going to say it is d by dt minus p by rho square d rho by dt. Okay. Now, I look at this minus d rho by dt. I will go and use my continuity equation which is out here. This is why I wrote this here, d rho by dt. If I put a minus sign, then it is equivalent to taking this part to the other side of the equation. So, it will just come out to be rho times del dot u. I will use that in there. So, I will simplify this to d by dt plus p by rho square into rho del dot u. One rho gets cancelled there. Okay. I have this particular form here. Now, I need to write a dE by dt, which is just talking about the internal energy of the fluid and not the total enthalpy, which is what we have been writing till now. So, now I need to split this total enthalpy from my full energy equation. For this, I have to think about what are the components of my energy equation. I am going to say I have my enthalpy plus kinetic energy as my total energy equation, where enthalpy is having internal energy plus p by rho. Okay. So, if I write a conservation equation for kinetic energy alone, which I can obtain by multiplying the momentum equation by another u vector dot product of it and then finding out what the final expression is, that comes out to be the kinetic energy conservation equation. We will not do that here, I will just give you the final expression. Of course, this has again been simplified by using continuity equation, so that density is outside even though it is used for compressible flows. I am putting u square by 2 because it is in that particular form of kinetic energy form per unit mass basis. This term comes out to be rho f b dot u plus del dot of tau tensor dot u vector plus pressure times del dot u minus there is a feed term which I did not want to go into details of it, but since it is in the equation I have to talk about it a little bit. That is called the dissipation of energy due to viscosity, okay, dissipation of kinetic energy due to viscosity in this case. Okay. We have written an equation for kinetic energy conservation alone, okay, where we did not talk about internal energy of the gas, it is just the kinetic energy part. Okay. What you are finding is kinetic energy change is due to external force doing work on the system on the particular fluid element, or shear forces doing work on the fluid element, or pressure forces doing work on the fluid element. This is actually pressure work on the fluid element. Okay. This is the divergence of the fluid element and this is the expansion of the fluid element multiplied by the pressure, that is like P dV work that is forming here, and then this is your energy removed from kinetic energy so that it enters into thermal energy. We will see that soon. Okay. This is the part which causes heating of the gas when there is viscosity. Okay. We will not go into details of it, it will also have some terms like I believe it is u dot del dot tau, that kind of form will be there. I do not want to get into the details of it, we will just ignore it for now. Okay. It is not needed except for this one particular place. So, if I subtract this from our original energy equation which we had before, then it is going to come to a point where I can write it as rho dE by dt is equal to minus del dot q minus p times del dot u plus v. Okay. Only these will be remaining. You will find that the viscous work is going to be internal and it will just sit in the total energy also. Okay. So, only thing remaining is this particular part. What we are now seeing is this is only the thermal part of the energy. Okay. When we look at the thermal part of the energy, we are finding that if there is net convergence of heat into the fluid element, then it increases. If there is net contraction of fluid element, del dot U is related to rate of expansion of the fluid element, minus of that is like compression of the fluid element, that is external work done on my fluid that can cause heating of the fluid, and this is the energy added from kinetic energy to thermal energy due to viscous effects. Okay. If you look at this previous equation and this equation, in the kinetic energy equation there is a minus phi, I did not write the term, but it is going to be negative, it is pulling out energy from kinetic energy, and here it is plus phi, it is adding that energy into this thermal energy. If you look at the total energy equation which we had before, I will go back to it once more, that is this one, we find that there is no phi in this particular thing. Why? It is just an internal rearrangement, it is taking from one pocket and putting it into the other pocket, so it is not there at all. This is the net energy, overall how much do I contain, that kind of thing is this one. Okay. In here if you look at this part, this is sitting only in my internal energy equation, this part is sitting only in my kinetic energy equation, this also sitting only in my kinetic energy equation, this term is hidden somewhere inside. Okay. It is sitting in that P dot del U kind of term. Okay. We won't worry about that part, we will see it, it will come up now. Okay. So, this is my internal energy equation. Okay. Now, I want to put this dE by dt inside here, and I have a rho here, we will multiply this entropy equation with rho, so that I will get rho dE by dt. So, I am going to finally have a form rho into temperature ds by dt is equal to, I will put rho into dE by dt, instead of that I will write this expression which will be minus del dot q minus p into del dot u plus v. I have this particular term, now I will write this particular thing, p by rho times del dot u. This is my net entropy equation. Okay. What is that? Oh, last term should have a multiplied by rho also, because I multiplied the whole expression with rho. While rho dE by dt was this term, that one should also be multiplied by rho, that p will get rho will get cancelled. So, I have this term. Now, you will find that this term and this term gets out, they are getting cancelled. Okay. So, I am finding that for my entropy to increase, it has to be through convergence of heat into the fluid element or through frictional heating of the fluid element. Okay. These are the two modes where I can have entropy increase in my fluid flow. Okay. All this point I have always used compressible, density was changing. It so happens that I used my continuity equation, so that the density always comes out of my derivatives, but I know that it is compressible flow. Okay. So, the essential part of this particular statement is that if I do not have heating of my fluid either by heat conduction or by viscous forces, I will not have any entropy change in my fluid flow. Okay. These are my predominant changes in entropy. Entropy changes are mainly due to this. Of course, we also know that there is one more way we can change entropy, that is through shocks in the flow, okay, which is just sitting inside this, which we could not talk about here. Okay. That will come as delta P naught, that will not be from here, that should come from the direct expansion of this term. Okay. If I expand it, we did this long back where we, I do not know where I have that expression right now, but we found that delta S by R was equal to log of T naught 2 by T naught 1 to the power gamma by gamma minus 1 multiplied by P naught 1 by P naught 2. We had one such expression. Okay. This is going to take care of that fluid mechanical way of increasing entropy. Okay. This is one more form of writing it. This is actually derived from this top equation. We won't go into the details of that right now. It was done, I believe, just after moving shocks discussion. Okay. So, we want to look at those particular two characteristics, that is, one is heating of the fluid element or viscous forces causing entropy change. Okay. So, we are going to deal with two types of flow fields now, where there is entropy change important. First one we will pick up friction flow, next one we will pick heating. But before that, I just wanted to give this small snippet of analytical work by an Italian engineer called Crocco. Okay. It is a nice point to give it here. It has to be given so that you will understand the connection between vorticity and entropy. Since we are anyway deriving gradients of entropy in my flow, etc., it is a good point to give it at this point. So, we will derive it the simplest way first, then we will give you the most complicated expression. Okay, that is the final result. It is also going to introduce you streamwise coordinate system. Okay. I am calling this as my streamline. I am using this kind of S, small s, while if I use the other S, this is entropy per mass. This is my streamwise distance coordinate system. Okay. So, I am having this as S, let us say this is my reference point I am picking, this is my n, the normal, stream normal coordinate system. Okay. So, I will say that if this is my point n comma s, this is going to be a delta n there. So, this point will be delta s here, sorry. This will be n comma s plus delta s, okay. While here it will be n plus delta n, this will be my delta n plus delta n and s, this will be n plus delta n, s plus delta s, that kind of coordinate system I am going to have. Now, let us say I have some particular velocity direction with respect to my previous original rectilinear coordinate system. Let us say this is having a theta xy coordinate system based, theta with respect to xy coordinate system, that is my velocity vector. Okay. If that is the case, then when I go from here to the next end point, it is going to be, again velocity vector will be parallel to that local streamline, which is this line, another S curve, and that angle is going to be theta plus dou theta by dou n times delta n, just a generalized form of writing it. For a small change in n, how much will be the change in theta is what this represents, and we will just keep it that way, very generalized form. Okay. And here this gap was delta s, I am going to say this is delta s plus dou by dou n of delta s times delta n. Okay, the change in delta s with delta n is what is shown there, that is this point to this point, the gap is there. Okay, just taking care of full details. Of course, we may not use all of them, and what will happen to velocity here, this velocity will be u, which is the value here, this is my velocity u. Okay. It will become u plus dou u by dou n times delta n. Okay. This will be the velocity at this point. Should I think about components of velocity? there is no components here because it is a streamwise coordinate system, which means all the velocity is going to be only along this S. There is no velocity component perpendicular to it because this is a streamline. Okay. So I can just talk about velocity always along this direction, there is no perpendicular component. So I have basically brought my problem down. I don't need to think about u as a vector, I will just think about u, and it looks as if it is a 1D problem finally, because it is going to be varying only inside the stream tube. Okay. Between any S and S plus delta n, n and n plus delta n, that particular thing is one set of stream tube, and my problem is 1D problem inside this, which means now I can use all the 1D equations. Okay. So we will write the 1D conservation equation for this. Whatever we have used all the time, we will just write it here, rho u times delta n. This is supposed to be rho u a is constant. When I say delta n here, this is the delta n is this length and unit depth inside. I am thinking 2D problem, it is unit depth inside. So delta n times 1 is what is given as area here. Similarly, momentum, now we have to be a little more careful, forces can act along this n direction also. So now I have to think about S momentum first, only along the S direction, S momentum equation, like we had x momentum and y momentum, right. So here it is S momentum equation. Now it can be written as rho u dou u by dou S equal to minus dou p by dou S. If you look at this, this is your acceleration of your fluid element, okay, inertial forces here, and that has to be compensated by the pressure force from here to here. The fluid is accelerating this way because I am going to say pressure here is higher than pressure here, so there is a dp by ds that is negative, and what is the net force acting, that will be minus of dp by ds times that area. I have divided by area throughout, that is this. This is basically your force balance, momentum increase is equal to the force, that is what is written there, or you think about it as F equal to ma kind of formula. Next one is normal momentum equation, where now I have to think about the streamline is curved and it is curving. If it is curving, then there is a force perpendicular to the velocity vector, that is when a flow streamline will turn, it is like a centrifugal force or centripetal force. Okay. So I will write an expression for that, that will be rho u square by r, this is your centripetal component, this should be given by minus of dou p by dou n. The normal force, if my pressure here is higher than pressure here, then my streamline will curve up. As the pressure goes from lower end to higher end, pressure decreases, which means my streamline will turn up. That is what this is showing here. Okay, minus of dou p by dou n is the net force upward, that is going to cause a centripetal acceleration. Okay, that is this term sitting here. Okay. Now I will just write, since we have this u by r, r is your radius of curvature, I will write this as in terms of theta, which we are given in the drawing, rho u square into 1 by r can be represented as dou theta by dou s, that happens to be the curvature. Okay. 1 by r is given as curvature, which is equal to dou theta by dou s. Okay. How does theta vary as I go this way? That talks about the curvature of this this particular curve S coordinate system. Okay. Now the only other thing left is energy. We will write the simplified form, simplest form, where we will say that there is no heat transfer, there is no viscosity, just for this Crocos theorem derivation alone. Okay. When we say that, we know that H naught is constant. This is the old 1D derivation, I am just writing it again. And in fact, in today's derivation also, you can say when you set those terms to be equal to 0, you just automatically get to this. Of course, I can now introduce, it may have a non-stationary flow where pressure may be changing with time. I could get that kind of dou p by dou t term here if I want to. Currently, we will keep it simplified. Okay, when we give you the generalized expression, I will give you the full thing. One more thing I need to tell here is, this is telling H naught is constant for every streamline S. It may so happen that this streamline can have a different H naught from this streamline. I did not tell anything about H naught is constant for all S. I just said H naught is constant along a particular S. That is all we know. 1D gas dynamics, we just know that inside a stream tube H naught does not change. It may change from one stream tube to the next one. Okay, that can still happen. So now I will go and write again entropy relation, where this S is entropy per unit mass. I will just directly go into PdV VdP, sorry, dH minus VdP, which can be expressed in terms of dH naught from the expression written there. dH naught minus U du will be your dH minus 1 by rho dP. I can write it like this. So from here I want to go and look at individual variation of entropy along S direction and N direction. So I will take this definition, this is for any particular change in S. So now I will go make it change only in one particular direction, T dou S by dou streamwise coordinate dou small s is equal to, I know that along streamwise direction dou by dou H naught is, I will just write it also, I guess, H naught by dou S, which is 0 because that is what we said is constant, okay, minus U dou U by dou S minus 1 by rho dou P by dou S. This is what we get. And now I will write the other one, stream normal direction, dou S by dou S. This is going to be equal to dou H naught by dou N minus U dou U by dou N minus 1 by rho dou P by dou N. I have these. Now we will just go back to this dou S by dou streamline. These, any problem? Oh sorry, yeah, this is dou S by dou N. Yes. Okay. Now we look at this dou S by dou S. What we see is from my momentum equation, S momentum equation, that is going to become 0. So if I take this rho 1 by rho here, this is equal to that other term, and the one is negative of the other, these two will give out to be equal to 0. So I will just say equal to 0 from S momentum equation. Okay, from S momentum equation, that is 0. That cannot be said about the other term. Okay, if you look at the other term, I can write something for dou P by dou N. Okay, that will be rho U square by R. Okay, even if I write it, that is not going to be 0, that term will just stay. So this is going to be equal to dou H naught by dou N minus U dou U by dou N plus U square by R. Okay, just have this particular form. Now since dou S by dou S is 0 and S can vary only along S or N, entropy can vary only along streamwise or stream normal direction, and we say it does not vary along streamwise direction, I can rewrite this partial derivative as total derivative now. Okay. Same thing can be done for H naught also, this can also be written as total derivative. Okay. If I do that, d ds by dn is equal to dh naught by dn plus u into u by r minus dou u by dou n. Okay. I will just say here that this term can be shown to be equal to minus of omega the vorticity vector. Okay. This is actually should be a vector, but since it is 2D problem, the vector is also always going to be pointing out of the board, and it is going to be having a negative value because in this case it will be pointing inside the board, into the board. Okay. So, I will just keep it as is. This is from definition of vorticity in streamwise stream normal coordinate system. You will get it to be this. We will just write it like this. So, I finally end up with a form. Let me check whether I made a mistake somewhere here. Minus will become plus on this side. I am not sure of this whether it is plus or minus. Okay. Okay, as of now I will assume this plus, it could be minus. Just a minute, we will just go through this. Dou ds by dn t ds by dn. I will just keep it as minus there, so it will become plus u omega is equal to dh naught by dn. Okay. We get to this expression. It looks like I have made one small mistake in my derivation, but I am not sure. So, I believe this should be minus omega here, but the expression seems to be correct finally. So, maybe I have made a mistake here or not made a mistake, I am not sure about this, whether it is minus or plus I am not sure. Okay. But this is the final expression I am getting here, but the physics I want to talk will not change here as of now. Okay. There might be a, this could be a minus or a plus currently, we will just leave it there. Physics I want to talk about is, if I have enthalpy gradients in my flow from one streamline to other streamline, that is in the normal stream normal direction, okay, then I may have entropy variation. That is one way of looking at it. Or if I am starting with constant enthalpy in all the streamlines, if I have constant enthalpy in all the streamlines, then if I have entropy gradient, then I will definitely produce vorticity in my flow. This is the important statement of Krokow's theorem. This is called the Krokow's theorem. Okay. If typically most of the fluid flows which we start or work with, we will always have dh naught by dn 0, and we also have dh naught by ds 0 that we already saw, that is h naught does not change along the flow streamline. So, I am going to say that since we started with enthalpy constant at the beginning, it is going to be remaining the same all through, except when there is if that is, again I made this 0, then I will produce vorticity in the flow if there is entropy gradient across streamlines, d by dn of s not equal to 0. If I have this not equal to 0, then I will definitely produce vorticity. This is the main statement of Krokow's theorem. Now, I will just write the full or more complicated expression for Krokow's theorem, then we will stop here. We will look at the implications of this next class. The full equation of Krokow's theorem is T gradient of S plus u cross del cross u is equal to gradient in H naught plus dou u by dou t. Okay. This is the full Krokow's theorem expression, where what we derived did not have any non-stationary term, we removed that part, and this is the most complicated form where this is your vorticity omega vector in this case. Okay. We have this particular term. What we are seeing again is, if I start with the isoenthalpic flow or home enthalpic flow if you are referring to some other books. Okay. Isenthalpic flow, then and I am having stationary flow, then I do not have these two terms, that is 0. Then if there is an entropy gradient in my flow, I will produce vorticity in the flow. Okay. This is the main statement from Krokow's theorem. We will keep it, we will look at examples of vorticity produced in the flow next class, and then start going into frictional flows and how to analyze flow with friction. Okay, this one small part I wanted to discuss also by today. There is not enough time, I do not want to hurry, we will do it next time. Okay. So, any question? And see people next class.